So for the second part of this getting ready lesson, we're going to focus on a lesson that we did way back in, I'm going to go with October. It would have been lesson 2.4 towards the end of unit 2, lesson 2.4, analyzing rational functions. A big part of what we're going to be doing with limits is we're going to go back and essentially redo lesson 2.4, but we're going to be changing up some of the vocabulary and a little bit of the notation. But there, you're hopefully going to notice there is a very strong resemblance between what we're going to be doing in these next few lessons and what we did way back when. Now, if you need a reminder, a summary of what we did way back in lesson 2.4 was given a rational function. I asked you to find the domain, vertical asymptotes, holes, horizontal asymptotes, slant asymptotes, x-intercepts, and y-intercepts. On that test for unit 2, there were a couple of questions where it was just basically list, here's a rational function, list out all of these pieces of information about that rational function. Recall that domain you find for a rational function, you find the domain by looking for the roots of the denominator, figure out where the denominator equals 0, and we would state the domain as all real numbers except x cannot equal these values because you can't have 0 in a denominator. The holes and the vertical asymptotes could be found as essentially classifying those roots of the denominator, those domain restrictions, as either a hole or a vertical asymptote. The factor that canceled was a hole, and the factor that didn't cancel is a vertical asymptote. Now, of course, that's if that factor is on the bottom. There could possibly be another factor on the top that didn't cancel, but if it's on the top, it's not a domain restriction, and thus it's not a vertical asymptote. If it's on the top, then it's an x-intercept. Remember, zeros on the bottom are undefined. Zeros on the top are just that. They're zeros. We also had a technique for finding horizontal and slant asymptotes, and that had to do with that whole top-heavy, bottom-heavy mess. If it was top-heavy, then you had a slant asymptote. We used synthetic division to find the slant asymptote. If the degree was bottom-heavy or the degree on top and bottom were the same, then we had horizontal asymptotes. So we had all different rules related to that. And of course, the y-intercept is just the constant term, or the ratio of the constant terms. You can also find a y-intercept simply by plugging in x equals 0. So, I'm not going to give any instruction here. If you need instruction, go back and rewatch lesson 2.4. I'm just going to ask you to pause the video here and try these two problems. Pause here, play when you're ready. All right, hopefully you either remembered how to do this or you went back and rewatched the lesson video for lesson 2.4 part 2. So we want to analyze the function by stating the domain, then identifying any holes, vertical asymptotes, and or intercepts. So looking at the first one, x squared minus 9 over 2x plus 6. We're going to start by factoring everything out. Top is a difference of squares, x plus 3x minus 3, and the bottom we can just pull out a 2 using the GCF method. To get the domain, don't cancel anything out yet. To get the domain, anytime the bottom is equal to 0, we have a domain restriction. I only have one variable on the bottom, which means I only have one domain restriction, and that's going to be at x equals -3. So domain is all real numbers, except x cannot equal -3. Remember, for a domain restriction, we'll say x cannot equal -3. Now, that domain restriction can either be a vertical asymptote or a hole. -3 cannot be the x-intercept because it's a domain restriction, and an x-intercept is a point that exists on the graph. -3 does not exist. So vertical asymptote or hole, vertical asymptote or hole, we figure that out by seeing if that x plus 3, which is where the -3 came from, does that x plus 3 cancel or not cancel? In this case, x plus 3 cancels, making x equals -3 a hole. Since there are no remaining variable-based factors on the bottom, that means there are no vertical asymptotes. X equals -3 is a hole. There are no vertical asymptotes. Now, back in Unit 2, I always had you describe the holes using the x equals notation, but I do want to point out a hole is a position on the graph. Unlike a vertical asymptote, which is an entire line on the graph, so you'd have to use the x equals notation. But for a hole, you could actually label this as a coordinate. The hole exists at a specific point. If I were to take -3 and take that x value and plug it in for x, that would spit out a y value that corresponds to that location. Now, the problem is if I plug in -3 into this version of the expression, -3 squared is 9, 9 minus 9 is 0 on the top, Negative 3 times 2 is negative 6. Negative 6 plus 6 is 0 on the bottom. I actually get 0 on top and 0 on bottom, so that doesn't actually tell me anything. I don't know what 0 over 0 is. We're going to have a whole lesson coming up soon about the concept of 0 over 0. Is it equal to 0 because 0 is on the top? Is it equal to undefined because 0 is on the bottom? Is it 1 because top and bottom are the same? 0 over 0 is actually unknowable. That's not an actual number. You cannot interpret any value from the statement 0 over 0. But if I take that negative 3, instead of plugging it in here, let's plug it in over here, the simplified version of the rational function. Notice, negative 3 minus 3, that's negative 6. And then negative 6 divided by 2 is negative 3. So we actually have an answer. When x equals negative 3, the y value is also negative 3. Pure coincidence, nothing special or significant going on there. Pure coincidence that it happened to come out as negative 3. But I can tell you that the hole on this graph is precisely at the coordinate negative 3, negative 3. I don't care if you present the hole as being at x equals negative 3, or if you present the hole as the coordinate negative 3, negative 3. Either is a correct answer. X-intercepts can be found using the remaining factors from the top. X minus 3 remained on the top, so x equals 3 is an x-intercept. Keep in mind an x-intercept could also be presented as a coordinate. Those are a little bit easier because intercepts always have 0 as one of their values. For an x-intercept, the y value is 0, and then for the y-intercept, the x value will be 0. To figure out the y-intercept, simply just plug in 0 for x. If I plug in 0 for x right here, I get negative 9 over 6. If I plug in 0 for x right here, I get negative 3 over 2. Both of those are exactly the same answer. I'm going to go with the simplified version. So the y-intercept is y equals negative 3 halves, or as a coordinate, it would be at 0, comma, negative 3 halves. Something you could also do to check your answer is pull out your calculator and graph it. Feel free to take a moment right now. Pause the video, play when you're ready. Grab your calculator, type in x squared minus 9 over 2x plus 6. When you graph it, you should be typing it in, looks like this. Make sure if you're not using the fraction key, then you need parentheses around the entire numerator and the entire denominator. So that would be parenthesis x squared minus 9, close parenthesis, divide, open parenthesis, 2x plus 6, close parenthesis, or just use the fraction feature as long as you have an updated calculator. And when you graph it, I'm graphing on the standard viewing window, negative 10 to 10, and I get something interesting. I get this picture right here, and you might think to yourself, hey, isn't that the graph of a line? And I would say, hey, yeah, it is, all right? Not all rational functions are those typical reciprocal functions. Notice we have no vertical asymptotes on this graph, so that's perfectly fine to have a line. If we take a look back up here, x minus 3 over 2, if I were to split that into two separate fractions, since I have a monomial denominator, x over 2 minus 3 over 2 is actually the expression 1/2 x minus 3 halves. That's y equals mx plus b. The y-intercept is at negative 3 halves, or negative 1.5, and we have a slope of 1 over 2. This is indeed the graph of a line, but it's not an entire line because there's a hole at x equals negative 3. If you trace negative 3 on your calculator just to make sure, trace negative 3, I'm going to get no answer for the y value because indeed there is no answer for this function. There is a hole at x equals negative 3. Negative 3 is not a point on the function. Negative 3 is the location of the absence of a point. So it makes sense that it would not be spitting out the y value. We can check the x-intercept by tracing x equals 3. Look at that, x equals 3, y equals 0. X-intercept is a point on the graph, so it should spit out the y value. And we can check the y-intercept by plugging in 0 for x. X equals 0, y equals negative 3 halves. You can always use your calculator to check these sorts of problems. Here's the second one. If you haven't already paused here to try it, go ahead and pause here, play when you're ready. Just like before, we're going to start by factoring everything out. Hopefully that wasn't an issue. Top factors this way, bottom factors that way. Domain restrictions are based on the denominator. Negative 3 and positive 1 are my restrictions, so all real numbers. X cannot equal negative 3 and 1. Those values can be classified as either a whole or a vertical asymptote. Which one cancels is the whole. So x equals 1 is going to be the whole. If you want to present that as a coordinate, just take x equals 1 and plug it into the simplified version. 2 plus 5, 1 plus 3, we have a whole at exactly 1 comma 7/4, but again, you don't need to give me the coordinate if you don't want to. And the vertical asymptote will be based on the factor on the bottom that did not cancel out. X plus 3 produces x equals -3. So this one will indeed have a vertical asymptote at x equals -3. X-intercept is going to be based on the factor that remained on the top. 2x plus 5 gives me an x-intercept of -5/2. And the y-intercept will just be based on the ratio of the coefficients. You can either go from the original or from the final. It gives you the same answer, 5/3. And just like we did before, I can take this and graph it in the calculator just to make sure that I'm right. So again, graphing over the standard viewing window, -10 to 10. Notice I have a vertical asymptote at x equals -3. I can check that just by tracing -3 and making sure that there is no output value for y. Same thing for the whole at x equals 1. At x equals 1, I don't visually see a hole in the graph, but when I trace 1 and see that there's no output value, I can interpret, well, it's definitely not a vertical asymptote, therefore it must be a hole in the graph at x equals 1. X-intercept at -5/2, so -5/2 is -2.5. That has a y output value, y equals 0. And the y-intercept, if I input 0, I should get out 5/3, which is exactly what I do. Now, before we move on any further, I want to take a moment and address something I said previously about this entire getting ready unit or lesson. A big part of what we're going to be doing in this limits unit is taking concepts that we learned previously and just repackaging them. For instance, wholes and vertical asymptotes. I'm going to go ahead and introduce you to some vocabulary I didn't use earlier in the year, but I'm going to start using at this point in the year, because when we talk about limits, we often use this vocabulary instead of the old vocabulary. The old Algebra 2 vocabulary of calling something a whole is nice, but in calculus, we don't actually call it a whole, we call it a removable discontinuity. The vertical asymptote is no longer called a vertical asymptote, although it is still technically a vertical asymptote. It's not wrong to call it a vertical asymptote, but a vertical asymptote is a type of non-removable discontinuity. I wonder why we call these removable and non-removable. Think about what it takes to identify a whole versus an asymptote. A whole is the factor that cancels. Vertical asymptote is the factor that did not cancel. Removable, non-removable. The x minus 1, I was able to remove that discontinuity, so x equals 1 is a removable discontinuity. The vertical asymptote is the factor that did not cancel, therefore it was non-removable. Now remember, 2x plus 5 also did not cancel, but 2x plus 5 was on the top, and thus 2x plus 5 did not represent a discontinuity. 2x plus 5 is continuous, not a discontinuity. Of the discontinuities, -3 and 1, x equals -3 and x equals 1 were discontinuities. Discontinuities can be classified as either removable or non-removable. And we're going to take a deeper dive into that vocabulary in the next part of this lesson, but in the meantime, I want you to stop the video here and practice just this concept.